All right, now we'll look at Newton's second law of motion, Newton's second law for rotational motion. Again, the idea is the following. For linear motion, here was Newton's second law, mass times force was equal to time rate of change of momentum. Okay, so the parallel for force is torque for rotational motion, and we'll show you that this is Newton's second law. And the parallel of linear momentum is angular momentum denoted by L. Okay. So the parallel of force is torque, and the parallel of linear momentum is that. And this is Newton's second law of motion for rotational motion. And so in the next few slides, we'll define torque and we'll define angular momentum and so on. Okay, so torque is defined as follows. So here's an object and it's fixed to rotate about this axis. So let's say, or we're calculating the torque about that axis. And for now, we'll say that it's rotating about that axis. So if you apply a force at this point, and that's the force you applied, this force will make the object rotate. Okay. Now, if you apply the force in this direction, it would not make it rotate. At this point, it'll make it rotate. If you apply the force like that, the same magnitude force will have a greater effect, rotational effect. If you apply the force in that direction, it would not make the object rotate. Okay, you can see all of that in this simulation. So I urge you guys to go see that. Okay, so the effectiveness of this force, like I said, with the same magnitude, depending on what angle you apply the force, it might make it rotate faster, slower, and so on. Okay, so again, if you apply the force at this point in this direction, the object would not rotate. So the effectiveness of the force in making the object rotate is measured by torque, and the torque is given by this cross product, R cross F. So for instance, if F was in this direction, R and F would be parallel to each other and the torque would be 0. And the rate of change of angular momentum would be 0. If this was at rest, it will remain at rest. Okay, so all that is included in this formula. Okay, so now let's define angular momentum. Okay, so there's that object again. We are calculating the angular momentum over that point. Okay, so here's this disk, and consider this little piece of the disk. That piece has that velocity. Okay, angular momentum of that point, of that little piece, is defined as R cross P. R, the distance from the point about which you're calculating the angular momentum, and it's R cross P. Okay, so that's how we calculate angular momentum. And the angular momentum, so it's a vector, and if you use the right hand rule, R cross P, there's P is in that direction, R cross P will give you angular momentum in this direction. And if you take the angular momentum of every particle and add them up, the total angular momentum of the object will be in that direction. Okay. So there's angular momentum, there's that term. And what one finds is torque is equal to rate of change of angular momentum. Okay. And here are some simulations that you can go check out. Okay. That will that'll illustrate some of these concepts. So in this slide goes through the derivation, and so I won't go through the derivation, but anyway, so here's what it's showing you. So here's a point particle, and we're calculating the torque and angular momentum about the origin. You apply a force on this point particle, and R cross F gives you the net torque, and R is there. The net force on it is rate of change of linear momentum of the object. And here's a little trick that's done. Dr by dt is velocity, and velocity is related to momentum, and that crossed with momentum, any vector crossed with itself So anyway, dr by dt is p over m. Any vector crossed by itself is 0. And so you can add that to this, and what ends up happening is the net torque can be shown to be equal to this. Okay, so that's what this thing is. So net torque, so what that equation is telling you is net torque from the chain rule is dr by dt cross p plus r cross dp by dt. Okay, except that this term is 0, so that would be 0, and this is that term. Okay, so the net torque is equal to that, which is equal to rate, and that is angular momentum, that's L. So the slide has shown you that the net torque is equal to rate of change of angular momentum. Okay. So that's the Newton's second law for rotational motion. Now, if you have a system of particles, the angular momentum of the system is this angular momentum of particle 1 plus angular momentum of particle 2, and it's just the sum of the angular momenta of each particle. And the rate of change of the angular momentum of the system of particles is the rate of change of angular momentum of each particle, and that's the torque acting on each particle, and you just sum them up. So if you sum up all the torques acting on all the particles, that's the net torque acting on the system. So this equation, just like Newton's second law that applied to a single particle and a system of particles, this equation applies to a single particle or a single object and a system of particles. Okay, so that's what this is telling you. Okay. Now, so it turns out that the torque and angular momentum depend on what point you're calculating those things about. Okay, so both torque and angular momentum depend on the choice of the origin of the coordinate system. However, the relationship between them is independent of the choice as long as the center of mass of the system is not accelerating. So this equation is valid no matter what point you calculate the angular momentum and torque about, okay, as long as it's the same for both of them. So this equation is independent of the choice of the origin, okay. That's as long as the center of mass is not accelerating. And if you calculate it about the center of mass, if you calculate both of these guys about the center of mass, then this equation is always valid, okay, whether the center of mass is accelerating or not, okay. All right. Yeah. So again, so that's what this slide is saying. This equation is valid for an axis passing through the center of mass, and external torque acting on the system equals rate of change of angular momentum regardless of the motion of the center of mass. So as long as you calculate everything about the center of mass, this equation is always valid, okay. Okay, so what this slide shows you is for a point particle moving like that in a circle, the angular momentum is equal to the mass of the object times the speed of the object times the radius of the orbit. Okay, so for a circular motion, the angular momentum is just mvr, for a point particle. Now, in this slide, what we'll see is the following. So here's Newton's second law for linear motion, and dp by dt, and this is equal to d by dt. P is m times velocity, and which is equal to, so using the chain rule, it's dm by dt times v plus m dv by dt. All right, and this is equal to dm by dt velocity plus m times acceleration. Okay, so in most cases, the mass of the object does not change. This is 0, and so what you see is Newton's second law stated like that. But the most general case is this. We've seen systems where the mass will change and this is not 0. So for instance, for a rocket motion, this term is not 0, okay? So then you have to use this equation. That's Newton's second law, okay? So we'll see the parallel of that for rotational motion. So here's Newton's second law for rotational motion is dl by dt. And what we'll show is, just like for the previous case, mass was constant. If moment of inertia is constant, then torque can be shown to be equal to I times alpha. Okay, and that's what we are going to see in the slides. Okay, all right. So that's what's shown here. So here's a disk, a rigid rotating object, and the angular momentum of this particle is Li. And if you take the sum, so the angular momentum of each particle, and add them up, what you find is for the angular momentum of this object, you get I, the moment of inertia, times the angular velocity. Okay. So for a rigid object rotating about a fixed axis, the moment of inertia is constant, and the angular momentum is I times omega, and the torque acting on it, since I is constant, is d. So torque is dl by dt, which is d by dt of I omega. And since I is constant, is I comes out d by dt of omega, which is I times alpha. Okay, so that's what's shown here. So torque is equal to I times alpha, and this is the parallel of force is equal to mass times acceleration. Okay, so that's what this is showing you. So as long as I does not change, the parallel of force equal to mass times acceleration is torque is I times alpha. Okay, so that's the special case. Okay. All right. So now is a good time to pause, and I'll let you guys ask questions if you have any.